To create pure white light, or to display full-color images on the screen you're looking at right now, you need to combine exactly 3 primary colors of light: red, green, and blue. Back in the 1960s, engineers quickly figured out how to make red and green light-emitting diodes, or LEDs. They put them in calculators and digital watches. But trying to create a blue LED proved incredibly difficult, a problem that left researchers stuck for nearly 30 years. The Planck-Einstein relation links energy to wavelength. Low energy produces red light. Blue requires a high-energy photon. To generate it, you need a semiconductor with a wide band gap, a strict energy threshold electrons jump across. For blue light, this is exactly 2.7 to 3.0 electron volts. Physicists knew gallium nitride naturally possessed this exact band gap. The problem was structural. When they tried to grow gallium nitride crystals using traditional melting methods, the molecular structures wouldn't align, resulting in crystals riddled with microcracks and defects. Because it was so fragile and difficult to produce, the vast majority of the scientific community abandoned gallium nitride entirely. Without a viable material to emit blue light, the development of highly efficient digital lighting came to a complete halt. But a few researchers refused to drop it. In the 1980s, working at Nagoya University, Isamu Akasaki and his student Hiroshi Amano decided to tackle the gallium nitride problem from a different angle. This diagram shows a process called MOCVD, metal organic chemical vapor deposition. It is a manufacturing technique that builds crystals layer by layer from chemical gases rather than trying to melt solid metals down. Inside this ultra-clean vacuum chamber, vaporized metal organics and ammonia gas are swept over a solid disk of pure sapphire, which is heated to over 1,000 degrees Celsius. When those gases hit the intense heat of the sapphire, their molecules break apart. The gallium and nitrogen atoms fall to the surface and physically bond to each other, assembling a crystal structure atom by atom. To prevent the GaN from fracturing, Akasaki and Amano first laid down a thin buffer layer of aluminum nitride on the sapphire. This provided a compatible atomic template for the gallium nitride to grow on, stopping the microcracks before they could start. Mastering this vapor deposition process proved that a flawless gallium nitride crystal could exist. They now had the physical canvas they needed to build a working diode. To make the crystal actually emit light, they had to create a P-N junction. This is a deliberate boundary between one section of the crystal that has extra electrons and another section that is missing electrons, leaving empty spaces called holes. This is how that junction works at the quantum level. When you apply voltage to the LED, you force electrons up into a high-energy state called the conduction band. The holes remain down below in a lower energy state called the valence band. Because nature prefers a state of low energy, those high-energy electrons will naturally fall across the forbidden band gap to fill the empty holes below.
Energy cannot be destroyed. The exact amount of energy the electron loses during that specific drop is released into the universe as a blue photon. Creating the whole side of this junction was notoriously difficult, but Shuji Nakamura discovered that simply heating the material in a specific way, a process called thermal annealing, allowed them to mass-produce this boundary efficiently. They finally had a working blue LED, but the light it produced was incredibly dim. The electrons were moving too fast, shooting right past the holes and releasing their energy as useless heat instead of light. To make the diode bright enough for commercial use, engineers had to stop the electrons from shooting past their targets. They needed to force the electrons and holes into a confined space until they collided. Nakamura solved this with a structure called a quantum well. A quantum well is a microscopic trap made by sandwiching a nanometer-thin layer of indium gallium nitride between 2 layers of pure gallium nitride. Because the middle layer has a lower band gap, it creates a steep valley in the energy landscape. When electrons and holes wander into this middle layer, they fall into the valley. Once inside, they lack the energy to climb back over the high walls of the surrounding material. Now, huge numbers of particles are crammed together in a highly confined space. With nowhere else to go, the probability of them colliding and recombining skyrockets, generating a blindingly bright blue light. By stacking alternating layers of these materials into a multiple quantum well, manufacturers created a microscopic gauntlet of traps. This design captures almost every passing electron, converting a massive percentage of the electrical current directly into brilliant light. In 1993, Nichia Corporation announced the successful mass production of the first commercially viable high-brightness blue LED. Coating these blue LEDs with a yellowish phosphor converts part of the light into red and green. When these wavelengths mix together, the result is bright, pure white light. Traditional incandescent bulbs convert about 4% of their electricity into light, wasting the rest as heat. These white LEDs convert over 50% of their electricity into visible light, leading to a massive global reduction in energy consumption and carbon emissions. The precise control over high-energy blue photons also gave engineers the tools to read data far more densely, leading to Blu-ray technology, and provided the missing color needed to build flat-screen televisions and high-resolution smartphone displays. In 2014, Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura were awarded the Nobel Prize in Physics for their persistence in pursuing a material the rest of the scientific community had given up on. By isolating a specific energy gap and building a microscopic trap to force electrons into it, these researchers solved a 30-year physics problem. Their work with gallium nitride retired the incandescent bulb and provided the high-efficiency light that powers our modern digital world.